Welcome back to the channel. Before we dive into tonight's journey, I want you to get comfortable. Maybe dim the lights, maybe put on those headphones, maybe settle into that favourite chair of yours. Tonight we're going on a journey through time, a journey that took thousands of years, involved hundreds of brilliant minds, and changed the course of human civilization forever. We're going to discover how electricity went from a mysterious natural phenomenon that terrified ancient peoples to the invisible force that powers every aspect of your modern life. And I do mean every aspect. Right now, as you're watching this, electricity is flowing through your device, through the circuits in your brain interpreting these words, through the servers hosting this video, through the power lines crisscrossing your neighbourhood. It's so fundamental to modern existence that we barely think about it anymore. Flip a switch, light floods the room. Press a button, your world connects to billions of others. But it wasn't always this way. Before we wind the clock back, I have one small favour to ask. If you like drifting off while we unpack the big stories of science and history, consider subscribing to the channel and leaving a like on this video. It helps these calm, long-form journeys reach more people who need a quiet corner of the internet to relax in. And if you feel like it, tell me in the comments where you're watching from tonight. Alright, if you're comfortable, let's step away from the glow of your screen for a moment and travel back to a world before light bulbs, before power plants, before anyone had a word for electricity at all. The story of electricity's discovery isn't the tale of one brilliant inventor having a eureka moment in a laboratory. It's not Benjamin Franklin standing in a thunderstorm with his kite, though we'll get to that famous scene. It's not Thomas Edison illuminating the world with his light bulb, though that's part of our story too. No, the real story of how electricity was discovered is much longer, stranger, and more fascinating than any single moment. It's a story that spans from ancient Greece to the battlefields of the late 19th century. It's a story of accidents and insights, of bitter rivalries and collaborative breakthroughs, of theories that seemed insane at the time but turned out to be revolutionary. So settle in. This is going to take a while, because to truly understand how we discovered electricity, we need to travel back more than 2,600 years, to a time when the very concept of electricity didn't exist, when natural philosophy was just beginning to emerge from mythology, and when a Greek philosopher made an observation that would echo through the millennia. The year is around 600 BCE. The place is Miletus, a prosperous Greek city on the coast of what is now Turkey. Ships arrive daily from ports across the Mediterranean and beyond, their holds filled with exotic goods, strange materials from distant lands. Among these materials is a substance the Greeks call electron, a beautiful golden yellow material that washes up on the shores of the Baltic Sea, far to the north. We know it today as amber, fossilized tree resin, that has been compressed and preserved for millions of years. The Greeks prized amber as a gemstone. They carved it into beads, pendants, ornaments. It was beautiful, certainly, but it also had an unusual property, one that a philosopher named Thales of Miletus found absolutely fascinating. Thales was one of the first natural philosophers in recorded history, a man who tried to explain the world through reason rather than mythology. He's remembered for many things: predicted a solar eclipse, theorized that water was the fundamental substance of all matter, supposedly fell into a well while stargazing and was mocked by a servant girl for being so concerned with the heavens that he couldn't see what was at his feet. But for our story, his most important contribution was a simple observation about amber. Thales noticed that when you rubbed amber with a piece of cloth, particularly wool or fur, something strange happened. The amber would attract small, lightweight objects, bits of feather, dust particles, tiny scraps of dried leaves. They would leap toward the amber as if pulled by an invisible hand. Today we understand this as static electricity, the same phenomenon that makes your hair stand up after you rub a balloon on it, or gives you a shock when you touch a metal doorknob after walking across a carpet in winter. But Thales had no such understanding. In his world, this was pure mystery, a property of matter itself that defied explanation. He didn't call it electricity. That word wouldn't be coined for another 2,200 years. He simply observed the phenomenon, recorded it, and moved on. But that observation, that single curious note about amber attracting feathers, planted a seed in the human consciousness. The ancient Greeks also knew about another mysterious force, magnetism. They had discovered lodestones, naturally magnetized pieces of iron ore called magnetite, which could attract iron. The Chinese had been using magnetic compasses for divination, and later for navigation. But for thousands of years, electricity and magnetism were thought to be completely unrelated phenomena, two separate mysteries of nature. In ancient Rome, the naturalist Pliny the Elder wrote about amber in his encyclopedic Natural History, completed around 77 CE. He repeated the observation about amber's attractive properties, but like Thales before him, he offered no explanation. It was simply another curiosity in a world full of wonders. The Roman poet Lucretius, in his philosophical poem De Rerum Natura, attempted to explain magnetic attraction through the atomic theory of Epicurus, proposing that invisible particles stream from magnets and created the attraction. But electricity, that remained unexplained, barely studied, a footnote in the Natural Histories. And then came the fall of Rome, and the long centuries that followed. During the medieval period in Europe, much of the ancient learning was preserved in monasteries and in the Islamic world. But little new investigation was conducted. The observations of Thales and Pliny were copied and recopied, but no one seems to have done much experimenting. The medieval worldview was more concerned with theology than with natural philosophy, and mysterious forces like magnetism and electrical attraction were simply accepted as part of God's inscrutable creation. It would take a renaissance, a rebirth of classical learning, and a new emphasis on observation and experimentation before anyone would seriously investigate these mysterious forces again. It would take, in fact, until the year 1600, when an English physician with a curious mind published a book that would change everything. Picture London in the year 1600. Queen Elizabeth I sits on the throne of England, her reign drawing to a close after more than 4 decades. Shakespeare is writing Hamlet. The Globe Theatre has just been built on the banks of the Thames, and in this city teeming with life, stinking with refuse, periodically ravaged by plague, lives a prosperous physician named William Gilbert. Gilbert was born in 1544 in Colchester, Essex, into a rising middle-class family. His father was a recorder, a legal officer, and young William received an excellent education. He attended Cambridge University, earning his Bachelor of Arts in 1561, his Master of Arts in 1564, and finally his Doctor of Medicine in 1569. He established a successful medical practice in London, eventually becoming president of the Royal College of Physicians, and, in 1601, royal physician to Queen Elizabeth herself. But medicine was not Gilbert's only passion. He was fascinated by natural philosophy, and in particular by 2 mysterious forces, magnetism and electricity. For nearly 2 decades, Gilbert conducted careful, systematic experiments, methodically testing every claim he could find about these phenomena in ancient and contemporary texts. He spent what was then an enormous sum of money, some £5,000, on his research, enough to buy 2 large warships of the Royal Navy. Why such interest? Gilbert had naval contacts, sailors who relied on magnetic compasses to navigate the seas. He likely wanted to understand the fundamental nature of this tool that was so vital to England's maritime power. But as he investigated magnetism, he couldn't help but notice electricity, that strange property of amber mentioned in the ancient texts. And so he began to experiment. The results of his investigations were published in 1600 in a book with a typically lengthy Latin title, De Manet, Magneticisque Corporibus, et de Mano Manete Tellure. In English, On the Magnet, Magnetic Bodies, and the Great Magnet of the Earth. This work, which we usually just call De Magnet, was revolutionary. It was the first major work of experimental science written in England, a systematic investigation of magnetism and electricity that established much of the terminology we still use today. For his experiments, Gilbert developed several ingenious instruments. One was a versorium, a small metal needle balanced on a pivot so it could rotate freely. When brought near a magnetized object or an object charged with static electricity, the needle would turn. Gilbert also created a terrella, a small spherical lodestone carefully crafted to represent the Earth. By mapping the behaviour of compass needles around this sphere, he demonstrated that the Earth itself was a giant magnet, a revolutionary insight that helped explain why compass needles pointed north. But for our story, the most important contribution of de Magnete was Gilbert's systematic investigation of electricity. He was the first to carefully distinguish between magnetic and electrical phenomena, proving they were different forces despite their superficial similarities. Both could attract objects at a distance, but they behaved very differently. Magnetism worked only on iron and a few other materials, while electricity could attract almost anything light enough. Magnetism wasn't affected by moisture in the air, while electrical attraction weakened in humid conditions. Gilbert also vastly expanded the list of substances that could be electrified through rubbing. The ancients had only known about amber, but Gilbert discovered that many other materials could be charged: diamond, sapphire, carbuncle, opal, amethyst, beryl, crystal, glass, sulphur, sealing wax, and many resins. He invented a term for these materials, calling them electrics, after the Greek word for amber, electron. And here, in de Magnete, in the year 1600, the word electric entered the English language. Gilbert had literally named electricity, though he didn't yet understand what it was. He thought electrical attraction was caused by a material effluvium, a sort of vapour that extended from electrified bodies and drew light objects to them. This was wrong, but it was a theory, an attempted explanation based on observation. It was science. Gilbert's influence was immediate and lasting. Galileo praised de Magnete. Johannes Kepler tried to incorporate Gilbert's magnetic theories into his explanation of planetary motion. Francis Bacon cited Gilbert's work as an example of proper experimental method. The book was reprinted in 1628 and again in 1633, spreading across Europe and sparking renewed interest in both magnetism and electricity. William Gilbert died in 1603, possibly a victim of the plague that swept London that year. He never saw the full impact of his work. He never knew that the unit of magnetomotive force would eventually be named the Gilbert in his honour, or that he would be remembered as the father of electrical science. But his legacy was secure. He had turned electricity from an ancient curiosity into a subject worthy of systematic investigation. After Gilbert, the pace of discovery quickened. In the 17th century, Otto von Guericke in Germany would build the first electric machine, a sulfur sphere that could be rotated and rubbed to generate static electricity. Francis Hawksby in England would improve on this design, creating more powerful static electricity generators that could produce spectacular sparks and glows. The phenomenon was becoming not just a subject for natural philosophers, but entertainment for aristocrats who would gather for demonstrations of electrical experiments. But all of this was still just static electricity, brief discharges and temporary charges. No one yet knew how to store electrical charge, how to create a sustained flow, how to harness this mysterious force for any practical purpose. That would require new breakthroughs, new instruments, new ways of thinking about electricity. And it would require a new generation of experimenters, men who would push the boundaries of knowledge further than ever before. By the middle of the 18th century, electricity had become something of a craze in Europe. Aristocrats and wealthy merchants would attend lectures where natural philosophers demonstrated electrical phenomena, producing sparks, making people's hair stand on end, and performing what seemed like magic tricks using static electricity. It was scientific inquiry, certainly, but it was also theatre. The breakthrough that really accelerated electrical experimentation came in 1745, when two men, working independently on opposite ends of Europe, discovered essentially the same device. In the German city of Pomerania, a cleric named Ewald Georg von Kleist found a way to store electrical charge. In the Dutch city of Leiden, scientist Peter van Musschenbroek made the same discovery. The device they created would become known as the Leyden jar, named after the Dutch city. The Leyden jar was deceptively simple. It consisted of a glass jar with a metal conductor inside, typically a nail or chain extending through a cork that sealed the jar. The outside of the jar was coated or wrapped with metal foil. You would charge the jar by connecting the inner conductor to a static electricity generator while holding the outer coating, or having it contact the ground. The glass acted as an insulator, keeping the opposite charges separated. When the inner and outer conductors were later connected through a circuit, the stored charge would discharge, often with an impressive spark. This was the first capacitor, the first way to store electrical charge and release it on demand. The jar could hold quite a substantial charge, enough to give a strong shock to anyone who touched both conductors at once. In fact, Musschenbroek, in his initial experiments, gave himself such a powerful shock that he wrote he would not repeat the experience for the whole Kingdom of France. The Leyden jar revolutionized electrical experiments. For the first time, researchers could work with stored electrical charge rather than having to generate it continuously. They could time their experiments, control their conditions, and most importantly, they could produce stronger electrical effects than had previously been possible. The jar became the standard piece of equipment in any electrical laboratory. In France, the Abbé Nollet performed spectacular demonstrations with Leyden jars. In one famous exhibition, he arranged 180 soldiers in a line, had them hold hands, then discharged a Leyden jar through them, making them all jump simultaneously. In another demonstration, he passed a shock through 700 monks arranged in a circle. This was science as spectacle, but it was also teaching people that electricity was a powerful, real force that could affect the human body. One of the most important electrical experimenters of this era was a Frenchman named Charles-François de Sistenay-Dufay. In 1733, Dufay made a crucial discovery. There appeared to be two types of electricity. He found that when glass was rubbed with silk, it acquired what he called vitreous electricity. When amber or other resins were rubbed with fur, they acquired resinous electricity. Most importantly, he observed that objects charged with the same type of electricity repelled each other, while objects with opposite types attracted each other. This was a fundamental insight. Dufay didn't know about positive and negative charges in the modern sense, but he had discovered the basic principle. Like charges repel, opposite charges attract. This simple rule governed all electrical interactions, though it would be decades before anyone understood why. Meanwhile, across the Atlantic Ocean, in the bustling colonial city of Philadelphia, a printer and writer and inventor was about to take electrical science in a bold new direction. His name was Benjamin Franklin, and he was going to prove that the sparks in a laboratory and the lightning in the sky were the same thing. Benjamin Franklin was 40 years old in 1746 when he first saw electrical demonstrations performed by a travelling lecturer named Dr. Archibald Spencer in Boston. Franklin was already a successful printer and publisher, already famous for Poor Richard's Almanac, already engaged in civic improvements and scientific pursuits. But when he saw those electrical experiments, something ignited in his mind. He was, he later wrote, much pleased with the novelty of the thing. He purchased Spencer's equipment when the lecturer left town, and he began conducting his own experiments in his Philadelphia home, turning part of it into a makeshift laboratory. His wife, Deborah, was reportedly less than thrilled with the constant buzzing, crackling, and shocking going on in her household. Franklin proved to be not just a skilled experimenter, but also a brilliant theorist. Where others saw electrical phenomena as disconnected curiosities, Franklin began to see patterns, principles, and underlying order. He corresponded extensively with Peter Collinson, a Fellow of the Royal Society in London, sharing his observations and theories in a series of letters that Collinson eventually published in 1751 as Experiments and Observations on Electricity. In these letters, Franklin proposed something revolutionary. He suggested that electricity was not two separate types, as Dufay had claimed, but rather a single electrical fluid that could be present in excess or deficiency. An object with extra electrical fluid was positively charged. One with a deficiency was negatively charged. This was the origin of our modern plus and minus terminology for electrical charge. Franklin also recognized the principle of conservation of charge. When you rubbed glass with silk, he proposed, you weren't creating electricity out of nothing. You were transferring the electrical fluid from one object to another. The glass gained electrical fluid and became positively charged, while the silk lost electrical fluid and became negatively charged. The total amount of electrical fluid remained constant. Now, modern physics has shown that Franklin's model wasn't quite right. Electricity isn't a fluid. It's the movement of electrons, tiny negatively charged particles that are part of atoms. And ironically, Franklin got the sign convention backwards. What he called positive is actually a deficiency of electrons, and what he called negative is actually an excess of electrons. But despite these details, Franklin's conceptual framework was remarkably useful, and remained the standard way of thinking about electricity for decades. But Franklin's most famous contribution to electrical science wasn't a theory. It was an experiment, one that has become legendary, though the details are often misunderstood and the date is uncertain. It's the experiment that supposedly took place in June 1752, though Franklin himself never recorded the exact date, and some historians have questioned whether it happened at all, or at least whether it happened the way the story is usually told. The experiment, of course, involved a kite, a key, and a thunderstorm. For years, Franklin and others had noticed the similarities between electrical sparks and lightning. Both produced light and noise. Both could kill. Both seemed to follow similar paths through conductors. As early as 1749, Franklin had written down a list of similarities between lightning and electricity. Lightning gives light. So does electricity. Lightning strikes the highest and most pointed objects. So does electricity. Lightning is attracted to water and metals. So is electricity. The list went on, but similarity doesn't prove identity. Franklin wanted proof. He proposed an experiment. Erect a tall iron rod on top of a high building or church steeple, with a man stationed in a small shelter near the base. When a thundercloud passed overhead, the rod would draw electrical charge from the cloud, and the man could collect it using a Leyden jar or other apparatus, proving that lightning was indeed electrical in nature. There was just one problem. Philadelphia didn't have any buildings tall enough for the experiment. Christ Church was planning to build a steeple that would work, but construction was slow. Franklin grew impatient, and then he had an idea. If he couldn't put an iron rod high enough, what if he sent one up into the air on a kite? The details of what exactly happened are murky. Franklin never wrote a detailed first-person account of the experiment. Our main source is Joseph Priestley's 1767 book, The History and Present State of Electricity, written 15 years after the supposed event, based on conversations with Franklin himself. According to Priestley, here's what happened. Franklin made a kite from a large silk handkerchief stretched across a frame of cedar wood. At the top of the kite, he attached a sharp wire to act as a lightning rod. The kite was flown using a hemp string, which would conduct electricity when wet. At the bottom of the hemp string, Franklin attached a silk ribbon, which would remain dry and act as an insulator, protecting him from shocks. Between the hemp string and the silk ribbon, he tied a metal key. When a thunderstorm approached, Franklin and his son William went to a field and flew the kite. Franklin stood in a doorway of a shed to keep the silk ribbon dry. They waited. And then, as the storm passed overhead, Franklin noticed the loose threads of the hemp string standing erect, repelling each other, the characteristic sign of electrical charging. When he brought his knuckle near the key, a spark jumped. Electricity from the sky. Franklin had collected it, stored it in a Leyden jar, and performed electrical experiments with it. The electrical fire from heaven was the same as the electrical fire in his laboratory. Lightning was electricity. Now, it's crucial to understand what Franklin did not do. Contrary to popular belief and countless illustrations, Franklin's kite was almost certainly not struck by lightning. If it had been, Franklin would have been killed. What Franklin detected was the electrical charge in the air around the storm cloud, what we now call the electric field. The kite and string acted like an antenna, collecting this ambient charge. It was dangerous enough. Several other experimenters who tried similar experiments in the following years were killed. But it wasn't the dramatic lightning strike of legend. Whether or not the experiment happened exactly as Priestley described, Franklin's theory about lightning being electrical was proven correct by other experiments. In May 1752, before Franklin's kite experiment, French scientists Thomas-François Dalibard and Monsieur Delors successfully performed Franklin's iron rod experiment, drawing sparks from storm clouds. In August 1753, a Swedish scientist named Georg Wilhelm Richmann was killed while attempting a similar experiment when he was struck by what appears to have been ball lightning. The practical outcome of all this research was Franklin's invention of the lightning rod. He proposed that sharp iron rods 8 to 10 feet long be mounted on the highest points of buildings and ships, with a wire running down to the ground or water. When lightning struck, the charge would be harmlessly conducted away, protecting the structure from damage. This was the first practical application of electricity, and lightning rods quickly spread across Europe and America, saving countless buildings from fire. Franklin's work on electricity earned him international fame. He was elected to the Royal Society, awarded the prestigious Copley Medal, and was honoured by universities across Europe. All this for a man who never had a formal university education, who learned science by reading books during his apprenticeship as a printer, who experimented in his spare time while running a business and engaging in politics. But Franklin's greatest contribution wasn't the lightning rod, or even the kite experiment. It was the conceptual framework he provided. His model of positive and negative charges, his principle of charge conservation, his terminology. These became the foundation for all future electrical research. He showed that electricity wasn't just a curiosity or a source of entertainment. It was a fundamental force of nature that could be understood through careful experiment and clear thinking. By the time of Franklin's experiments, electricity had become a hot topic in scientific circles. Experimenters across Europe and America were generating sparks, charging Leyden jars, and trying to understand the nature of this mysterious force. But all of it was still static electricity. No one had yet discovered how to create a continuous flow of electrical current. No one had built a battery. That breakthrough would come from an unlikely source. A dispute between two Italian scientists about whether dead frogs' legs could generate electricity. Luigi Galvani was born in Bologna, Italy, in 1737, into a world where science and medicine were beginning to transform but were still heavily influenced by ancient theories and religious dogma. He studied medicine and philosophy at the University of Bologna, graduating in 1759 with a degree in both fields. By 1762, he was already lecturing at the Academy of Sciences in Bologna, and he spent the next 3 decades building a reputation as a skilled anatomist and researcher. Galvani's early work focused on the anatomy and physiology of animals, particularly birds and frogs. In the 1770s, he became interested in a new field called medical electricity, the study of how electricity affected living tissues. This wasn't entirely new. Researchers in the 1760s and 1770s had already shown that electrical shocks could stimulate muscles and nerves, but Galvani brought unprecedented rigour and systematic method to these investigations. The experiments that would make Galvani famous began around 1780, though the story of their discovery has become somewhat mythologized. According to some accounts, Galvani's wife noticed that a dissected frog's legs would twitch when touched by a scalpel at the same moment that a nearby electrical machine sparked. According to other versions, one of Galvani's assistants accidentally touched a brass hook to a frog's crural nerve while an electrical machine was running and observed the legs contract violently. However the discovery actually happened, Galvani became fascinated by this phenomenon. He prepared hundreds, perhaps thousands, of frogs for study. His prepared specimens consisted of frog legs severed at the base of the spine, with the sciatic nerves carefully exposed. These preparations were the core tool of his research for the next decade. Galvani discovered that he could make the frog legs contract in several ways. If he touched the exposed nerve with a metal probe connected to an electrical machine or a Leyden jar, the legs would kick. This wasn't surprising. Electrical stimulation of muscles was already known. But then he discovered something more puzzling. One day, Galvani hung several prepared frog legs on an iron railing in his garden, using brass hooks pushed through their spinal cords. He was studying the effects of atmospheric electricity, lightning during storms, but he noticed that the legs would sometimes twitch even when there was no storm, no lightning, no obvious source of electricity. Specifically, the legs contracted when the brass hook touched the iron railing. Galvani experimented systematically. He found that he could reliably produce contractions by forming a circuit with two different metals touching both the nerve and the muscle. The effect was strongest with certain combinations of metals, particularly when one was copper or brass and the other was iron. The effect also worked better in certain conditions, when the frog was fresh, when the circuit was complete, when the metals were in good contact. In 1791, after more than a decade of research, Galvani published his findings in a treatise titled De Viribus Electricitatis in Motu Musculari Commentarius, or Commentary on the Effect of Electricity on Muscular Motion. In this work he proposed his theory: animals possess an intrinsic electricity, which he called animal electricity, that flows through the nerves and activates muscles. The muscles, he suggested, act like Leyden jars, storing this electrical fluid. The nerves are the conductors. When the circuit is completed, the stored electrical fluid discharges, causing muscular contraction. The metals, in Galvani's view, were simply completing the circuit, allowing the animal electricity to flow. They weren't generating the electricity. They were just providing a path for the frog's own electrical fluid to move from nerve to muscle. This theory sparked immediate excitement and controversy. On the one hand, it seemed to provide an explanation for how nerves controlled muscles, solving a problem that had puzzled natural philosophers since ancient times. The idea that animals had their own form of electricity was revolutionary and seemed to fit the observations. On the other hand, the theory raised questions. Where did this animal electricity come from? How was it generated? Why did different metals produce different effects? And was Galvani certain that the electricity was coming from the frog and not from somewhere else? These questions troubled one of Galvani's colleagues, a physicist from the University of Pavia named Alessandro Volta. Volta initially accepted Galvani's theory and even reproduced his experiments. But the more Volta thought about it, the more doubts he had. Volta was an expert on electricity and particularly on static electricity. He began to suspect that Galvani had misidentified the source of the electrical current. What if, Volta wondered, the electricity wasn't coming from the frog at all? What if it was being generated by the contact between the two different metals? What if the frog's leg was simply a sensitive detector of electrical current, not the source of it? Thus began one of the great scientific controversies of the late 18th century, a debate that would divide the scientific community, produce bitter arguments, and ultimately lead to one of the most important inventions in the history of electricity. Alessandro Giuseppe Antonio Anastasio Volta was born in 1745 in Como, a small city in northern Italy. His family was part of the minor nobility, cultured but not particularly wealthy. Young Alessandro showed an early interest in natural philosophy and particularly in electricity. Despite family pressure to enter the priesthood, he pursued science, and by his mid-20s he had already invented an improved electrostatic generator. In 1774, at the age of 29, Volta was appointed Professor of Physics at the Royal School in Como. A year later he invented the electrophorus, a device for generating static electricity that was more practical than previous designs. This invention earned him recognition across Europe. In 1779, he was appointed Professor of Experimental Physics at the University of Pavia, a position he would hold for the rest of his career. When Volta first heard about Galvani's experiments with frog legs, he was intrigued. He replicated the experiments and initially agreed with Galvani's interpretation. But Volta's expertise was in electricity, and the more he worked with the phenomenon, the more sceptical he became of the animal electricity theory. Volta noticed something crucial. The muscular contractions were strongest when two different metals were used. If you used two pieces of the same metal, the effect was much weaker or non-existent. This suggested that the electricity wasn't coming from the frog but from the interaction between the dissimilar metals. To test this hypothesis, Volta began a series of experiments. He tried different combinations of metals. He found that zinc and copper produced the strongest effect, followed by zinc and silver, zinc and gold, and so on. He could even arrange the metals in order of their effectiveness in producing contractions, what he called the electromotive series. Then Volta did something that Galvani had never tried. He eliminated the frog entirely. He placed a piece of cloth soaked in salt water or weak acid between two different metal discs, one of zinc and one of copper. When he touched the two outer faces of this sandwich with his fingers or with a metal wire, he felt a weak tingle, a slight shock. The metals were generating electricity without any animal tissue at all. In his laboratory, Volta must have had a moment of profound realization. The frog's leg in Galvani's experiments wasn't generating electricity, it was detecting it. The frog was, in modern terms, a biological sensor, extraordinarily sensitive to even tiny electrical currents. The electricity was coming from the contact between dissimilar metals in the presence of a moist conductor. It was, as Volta called it, metallic electricity, not animal electricity. But a single pair of metal discs produced only a very weak current, barely detectable even by the sensitive frog's leg. Volta realized that if he wanted to produce a more substantial effect, he would need to find a way to increase the electrical output. And here he had another brilliant insight. What if he stacked multiple pairs of discs? In 1799, Volta built his masterpiece, the device that would change the world. He called it a pile, which in Italian simply means a stack. We call it the voltaic pile, or more commonly the battery. It consisted of a vertical column of alternating zinc and copper discs. Later, he found that silver worked even better than copper, with pieces of cloth or cardboard soaked in salt water, or dilute acid placed between each pair of discs. Each pair of discs, separated by the moist conductor, formed what we would now call a cell. By stacking multiple cells in series, Volta found that he could greatly multiply the electrical effect. A pile of 20 or 30 pairs of discs could produce a substantial shock, could generate visible sparks, could produce all the effects that previously required large static electricity machines and Leyden jars. But there was a crucial difference. The static electricity from machines and Leyden jars was a one-time discharge. Once the Leyden jar released its charge, it was empty. It had to be recharged before it could be used again. Volta's pile incredibly produced a continuous current. As long as the moistened cardboard stayed wet and the chemical reactions continued, electricity flowed from the pile in a steady stream. This was revolutionary. For the first time in human history, there was a reliable, steady source of electrical current. For the first time, experimenters could work with flowing electricity rather than just static charges and brief discharges. On March 20th, 1800, Volta wrote to Sir Joseph Banks, President of the Royal Society in London, describing his invention. The letter was read to the Society and published in their Philosophical Transactions. The Voltic pile was announced to the world. The response was immediate and dramatic. Within weeks, experimenters across Europe were building their own Voltic piles and discovering new phenomena. In England, William Nicholson and Anthony Carlisle used a Voltic pile to decompose water into hydrogen and oxygen, discovering electrolysis. Humphrey Davy at the Royal Institution began using massive voltaic piles to decompose compounds and isolate new elements, including sodium, potassium, calcium and magnesium. In 1801, Volta was invited to Paris to demonstrate his pile to Napoleon Bonaparte and the French Academy of Sciences. Napoleon was so impressed that he awarded Volta a gold medal, a substantial pension, and appointed him a Count of the Kingdom of Italy. The unit of electrical potential, the volt, would eventually be named in his honour. But what about Galvani? The debate between Galvani and Volta over the source of electricity in the frog experiments had become quite heated. Galvani, feeling that he couldn't adequately defend his theory himself, entrusted his nephew Giovanni Aldini with the task of promoting the theory of animal electricity. Aldini travelled across Europe performing dramatic demonstrations, including passing electrical current through the corpses of executed criminals, making their limbs move and their faces contort in what seemed like a grotesque parody of life. These demonstrations even inspired Mary Shelley's novel Frankenstein, with its theme of reanimating the dead through electricity. In his final years, Galvani tried to prove his theory by performing experiments without using any metals at all. He found that he could sometimes produce muscular contractions by connecting different parts of a frog's body directly together, or by using moistened conductors rather than metal wires. These experiments did suggest that there was some form of electricity intrinsic to living tissue. But without the recognition and acclaim that Volta received, without the dramatic practical success of the Voltic pile, Galvani's work was overshadowed. Luigi Galvani died in 1798, poor and largely forgotten, his academic position stripped from him for refusing to swear an oath of allegiance to the French-backed Cisalpine Republic. He never saw his ideas vindicated, but history would prove that both men were partially right. Volta was correct that the frog legs in the original experiments were not generating the electricity. The contact between dissimilar metals was, but Galvani was also correct that animals do generate their own electricity. Every nerve impulse, every heartbeat, every thought in your brain is fundamentally an electrical phenomenon. Galvani had discovered bioelectricity, the electrical nature of nerve and muscle function, even if he had misidentified its source in the specific case of his metal and frog experiments. The legacy of both men is profound. Galvanism, the term Volta himself coined to describe the use of chemical action to produce electricity, gave us not just our understanding of how batteries work, but also our understanding of how our own nervous systems function. And Volta's pile was the ancestor of every battery that has ever been built, from the batteries in your smartphone to the massive battery banks in electric vehicles. But the Voltic pile, revolutionary as it was just the beginning. With a reliable source of electrical current available, scientists could now investigate electricity in entirely new ways. They could explore how electricity moved through wires, how it created heat and light, how it interacted with magnets, and that last discovery, the connection between electricity and magnetism, would prove to be one of the most important insights in the history of physics. The man who would make that discovery was a bookbinder's apprentice from London, who would become one of the greatest experimental physicists of all time. Michael Faraday was born in 1791 in Newington Butts, a poor district of London. His father, James, was a blacksmith, often in poor health and unable to work regularly. The family frequently struggled with poverty. Young Michael had little formal education, basic reading, writing and arithmetic, but nothing more. At the age of 14, like many poor boys of his time, he was apprenticed to a trade. In Faraday's case, he was sent to work for George Rebow, a bookbinder. This apprenticeship, which would last 7 years, changed Faraday's life. Reibau was a kind master who encouraged his young apprentice to read the books they were binding, and Faraday read voraciously. He read everything he could get his hands on, but he was particularly drawn to books on science. One book made an especially deep impression, The Improvement of the Mind by Isaac Watts, which taught him how to learn and how to think. Another crucial book was Conversations on Chemistry by Jane Marcet, which introduced him to the wonders of chemistry and natural philosophy. Faraday didn't just read. He tried to reproduce the experiments described in the books, setting up crude laboratory equipment in his tiny room. He attended public lectures on science whenever he could scrape together the entrance fee. And in 1812, when he was 21, a customer of the bookshop gave him a gift that would change everything: tickets to 4 lectures by Humphrey Davy at the Royal Institution. Davy was the most famous scientist in England, a brilliant chemist who had isolated new elements using voltaic piles, and who was a masterful public speaker. Faraday attended all 4 lectures, took detailed notes, and bound them into a beautiful book. Then, with almost unbelievable audacity for a working-class apprentice, he sent the book to Davy with a letter asking for a job as his assistant. Davy's response was kind but discouraging. There were no positions available. But then, a few months later, one of Davy's assistants was fired for getting into a fight. Davy remembered the young bookbinder with the careful notes and the earnest letter. In 1813, Michael Faraday, now 22, was hired as a laboratory assistant at the Royal Institution. Faraday's rise was meteoric. He proved to be not just skilled with his hands, good at building and maintaining equipment, but also insightful, creative, and tireless in his experimental work. By 1821, he was already publishing important research, and in that year, he made his first major discovery in electricity. A Danish physicist named Hans Christian Ørsted had just discovered something astonishing. When an electrical current flowed through a wire, it caused a nearby compass needle to deflect. This was the first clear demonstration that electricity and magnetism were connected. Scientists across Europe were trying to understand this electromagnetism. Faraday, working with this new phenomenon, built 2 devices that produced continuous circular motion from the interaction of electricity and magnetism. One used a wire hanging from a pivot. When current flowed through the wire and a magnet was placed beneath it, the wire rotated continuously around the magnet. The other used a suspended magnet that rotated around a current-carrying wire. These were the first electric motors, crude but functional, converting electrical energy into mechanical motion. But Faraday's greatest discovery was still 10 years away. Throughout the 1820s, he worked on chemistry, investigating new compounds, improving the technology for producing optical glass. But he kept returning to the problem of electromagnetism. Ørsted had shown that electricity could produce magnetism. Could magnetism produce electricity? Could a magnet somehow generate an electrical current? Many people had tried and failed to demonstrate this effect. Faraday himself had tried numerous experiments without success. But on August 29, 1831, he finally succeeded. Faraday had wound 2 coils of insulated wire around opposite sides of an iron ring, creating what was essentially the first transformer. One coil was connected to a voltaic pile, a battery. The other coil was connected to a galvanometer, a sensitive device that could detect small electrical currents by the deflection of a magnetic needle. Faraday's logic was this: if he passed current through the first coil, it would magnetize the iron ring. If that magnetism could somehow produce electricity in the second coil, the galvanometer would register it. He closed the switch on the battery circuit, sending current through the first coil, and indeed the galvanometer needle jumped, indicating a current in the second coil. But then something strange happened. The needle returned to 0 almost immediately, even though the current was still flowing in the first coil, and when Faraday broke the circuit, turning off the current in the first coil, the galvanometer needle jumped again, but in the opposite direction. This was electromagnetic induction. Faraday had discovered that a changing magnetic field could induce an electrical current in a nearby conductor. It wasn't the steady magnetic field itself that produced the current, it was the change in the magnetic field. When he turned the current on, the magnetic field in the iron ring increased, and that change induced a momentary current in the second coil. When the field reached its steady state, the induced current stopped, and when he turned the current off, the collapsing magnetic field again induced a current, but in the opposite direction. Over the following months, Faraday explored this phenomenon thoroughly. He found that he could induce current by moving a magnet near a coil of wire, or by moving a coil near a magnet, or by varying the strength of an electromagnet. Any change in magnetic field through a loop of wire would induce an electrical current in that wire. On October 17th, 1831, Faraday made another breakthrough. He wound a coil of wire around a paper tube and connected the ends of the coil to a galvanometer. Then he pushed a bar magnet through the tube. As the magnet moved through the coil, the galvanometer registered a current. When he pulled the magnet out, a current flowed again, but in the opposite direction. When the magnet was stationary, no current flowed. This was the principle of the electrical generator. If you moved a magnet back and forth through a coil of wire, or rotated a coil of wire in a magnetic field, you could generate a continuous electrical current. Mechanical motion could be converted into electricity. It was the reverse of the electric motor. Instead of using electricity to create motion, you could use motion to create electricity. A few months later, Faraday built the first true generator, a device he called a disc dynamo, or the Faraday disc. It consisted of a copper disc mounted on an axle between the poles of a strong magnet. When you rotated the disc, electrical current flowed from the centre of the disc to its edge, where it could be collected by a brush contact. The current was weak, but it was there, continuous and reliable, generated purely by mechanical rotation in a magnetic field. Faraday had discovered the fundamental principle that would eventually power the world. Every electrical generator in existence, from the massive turbines in power plants to the alternator in your car, operates on the principle of electromagnetic induction that Faraday discovered in 1831. Every transformer, every induction coil, every electrical system that steps voltage up or down uses his principle. But Faraday didn't stop there. He continued to investigate electromagnetism for decades, making discovery after discovery. In 1845, he discovered that a magnetic field could affect the polarization of light passing through. Certain materials, the first demonstration that light and electromagnetism were connected. He introduced the concept of lines of force, extending through space around magnets and electric charges, an intuitive way of visualizing fields that later physicists, particularly James Clerk Maxwell, would formalize into mathematical field theory. Faraday was a deeply humble man. Despite his fame and his revolutionary discoveries, he remained modest, attributing his success to hard work and careful observation rather than genius. He refused a knighthood from Queen Victoria, preferring to remain plain Mr. Faraday. He continued to give free Christmas lectures for young people at the Royal Institution, wanting to share the joy of science with the next generation. Michael Faraday died in 1867, at the age of 75. The unit of electrical capacitance, the farad, is named in his honour. But his true legacy is much greater than any unit of measurement. Faraday transformed our understanding of electricity and magnetism. He showed that they were two aspects of the same phenomenon. He demonstrated that these invisible forces extended through space, that they could be described by fields rather than just by the action of one object on another at a distance. And most practically, Faraday showed the world how to generate electricity. Before his work, electricity was a laboratory curiosity, something produced by chemical batteries or by rubbing materials together, something that had no obvious large-scale application. After his work, it became clear that electricity could be generated mechanically, in any quantity desired. and that this electrical energy could be transmitted through wires and used to do work, to create light, to power machines. But generating electricity was only half the problem. The other half was distributing it, getting electrical power from where it was generated to where it was needed. And that problem would set the stage for one of the most intense technological and business rivalries of the late 19th century, a battle that would pit some of the greatest inventors and industrialists against each other in what came to be known as the War of the Currents. By the 1880s, the stage was set for the electrical revolution. Scientists understood the basic principles of electricity and magnetism. They knew how to generate electrical current using generators based on Faraday's principles. They knew how to transmit that current through wires. And inventors had begun to create practical devices that used electricity, most notably the incandescent light bulb. Thomas Alva Edison, already famous for inventing the phonograph and improving the telegraph, developed the first practical incandescent light bulb in 1879. But Edison understood that the light bulb alone wasn't enough. You needed a whole system, generators to produce electricity, distribution networks to deliver it, meters to measure usage, and most importantly, a business model to make it all profitable. Edison's solution was direct current, or DC. In a DC system, electrical current flows steadily in one direction, from the generator through the wires to the devices and back. Edison built the first commercial power station at Pearl Street in New York City in 1882. It was a remarkable achievement, the first central station to provide electrical power to multiple customers. Within a year, Edison's company had lit hundreds of lamps in Lower Manhattan. But Edison's DC system had a fundamental problem. It couldn't transmit power over long distances. Electrical current flowing through a wire encounters resistance, and that resistance causes energy loss as heat. The amount of power lost depends on the square of the current. If you double the current, you quadruple the power loss. To minimize these losses, you need to keep the current low. But Edison's DC generators produced electricity at relatively low voltage, around 110 volts, which meant relatively high current for any given amount of power. This meant substantial power losses over even short distances. The practical result was that Edison's power stations could only serve customers within about 1 mile. Beyond that, the power losses became too great. Every square mile of city needed its own power station, which was expensive and inefficient, especially in less densely populated areas. Enter the competition. In 1886, a wealthy industrialist named George Westinghouse, who had made his fortune inventing the air brake for railroads, founded the Westinghouse Electric Company. Westinghouse had seen European demonstrations of alternating current or AC systems, and he realized that AC had enormous advantages over DC. In an AC system, the current doesn't flow steadily in one direction. Instead, it alternates, flowing first one way, then reversing and flowing the other way, typically 60 times per second in the United States. This might seem like a pointless complication, but it had a crucial advantage. AC voltage could easily be transformed, stepped up or down, using a device called a transformer. Here's why this mattered. To transmit power over long distances with minimal losses, you want low current and high voltage. But for safety and practical use in homes and businesses, you want low voltage. With AC, you could solve both problems, generate power at moderate voltage, use a transformer to step it up to very high voltage for transmission, then use transformers near the end users to step it back down to safe, usable levels. This meant that a single AC power station could serve customers dozens of miles away. You didn't need a power station every mile. You could build one large, efficient generator and distribute its power across a wide area. The economics were dramatically better than Edison's DC system. Westinghouse hired talented engineers, including William Stanley, who developed an improved transformer design. In 1886, they installed the first commercial AC power system in Great Barrington, Massachusetts. It worked beautifully, lighting 23 businesses with minimal power loss over 4,000 feet of wire. By the end of 1887, Westinghouse had 68 alternating current power stations across America, rapidly approaching Edison's 121 DC stations. Edison was not pleased. He had invested heavily in DC technology. His patents, his generators, his entire business model was based on DC. The success of AC threatened to make all of that obsolete. Edison fought back with every tool at his disposal. He published pamphlets arguing that AC was dangerous, that its high voltages posed an unacceptable risk of electrocution. He lobbied legislators to pass laws limiting electrical systems to low voltages, which would have effectively banned AC, and most notoriously, he staged public demonstrations where animals, including dogs, cats, a horse, and even an elephant, were killed using AC electricity, supposedly to demonstrate its deadly nature. Edison even got involved in the development of the electric chair for execution of criminals, suggesting that AC current be used. His company secretly funded the design of the device, hoping to associate AC with death in the public mind. One Edison employee even coined the term Westinghoused as a synonym for electrocuted, though it never caught on. Westinghouse fought back, but not with fear-mongering. He focused on the technical and economic advantages of AC. He demonstrated that AC could be safe if proper precautions were taken. He installed AC systems in homes and businesses, showing that they worked reliably. And in 1888, he made a crucial acquisition. He bought the patents for an AC induction motor designed by a brilliant Serbian-American inventor named Nikola Tesla. Tesla deserves special mention in this story. He had worked briefly for Edison in 1884, after immigrating to America. Edison asked Tesla to redesign his DC generators to make them more efficient. Tesla did so brilliantly, but then he tried to interest Edison in a radical new idea, using alternating current. Edison dismissed the idea as impractical, and according to Tesla, refused to pay him a promised bonus for his work on the generators. Tesla quit in disgust. For the next 2 years, Tesla struggled to start his own company, at one point reduced to digging ditches to survive. But he continued to develop his ideas about AC. He envisioned not just using AC for lighting, but using multiple phases of AC to create rotating magnetic fields that could drive motors. In 1887, he demonstrated a working polyphase AC motor, and in 1888, Westinghouse bought the patents for $60,000 in cash and stock. This was the missing piece of the AC system. Edison's DC motors were well developed and practical, but AC motors had been problematic. Tesla's polyphase design solved the problem, providing smooth, efficient motors that could run on AC power. Now AC had everything: efficient long-distance transmission, safe low-voltage usage, and practical motors. It was a complete system. The War of the Currents reached its climax in 1893 at the World's Columbian Exposition in Chicago, a massive World's Fair celebrating the 400th anniversary of Columbus's voyage to America. The organisers needed to light the fair, and they invited bids from both Edison's company, now called General Electric after a merger, and from Westinghouse. General Electric bid $554,000 to light the fair using DC. Westinghouse bid $399,000 to do it with AC. Westinghouse won the contract, and when the fair opened, it was a dazzling showcase for AC power. Hundreds of thousands of light bulbs illuminated the fairgrounds, powered by massive Tesla-designed AC generators. More than 27 million people visited the fair, and they all saw the brilliant, safe illumination provided by alternating current. The demonstration was conclusive. AC was not dangerous. It was not impractical. It worked, and it worked beautifully. The next year, Westinghouse won another crucial contract, building the generators for the hydroelectric power plant at Niagara Falls. This was one of the most ambitious engineering projects of the era, harnessing the immense power of the falls to generate electricity. When the plant came online in 1896, it transmitted AC power 26 miles to Buffalo, New York, a feat that would have been impossible with DC. By this point, even General Electric had acknowledged reality. The company began manufacturing AC equipment using designs licensed from competitors. Edison himself had lost control of the company that bore his name. The War of the Currents was over. AC had won. But we should be careful about simplifying this story into a morality tale of visionaries versus reactionaries. Edison wasn't a fool, and DC wasn't inherently inferior. For local distribution, for battery-powered devices, for many applications, DC was and is perfectly good. The issue was long-distance transmission, and for that, in the era before modern power electronics, AC was indeed superior. Edison's mistake wasn't in developing DC, it was in refusing to adapt when the advantages of AC became clear. And what of Tesla? Despite his brilliant inventions, he was never as successful as Edison or Westinghouse. He signed away royalty rights to his AC motor patents to help Westinghouse financially during the War of the Currents. He pursued increasingly speculative projects like wireless power transmission that never became practical. He died in 1943, living alone in a New York hotel room, feeding pigeons, largely forgotten by the public. Only later would he be recognized as one of the greatest inventors of the electrical age. The victory of AC shaped our modern electrical grid. To this day, electrical power is generated at power plants, stepped up to very high voltages for transmission over long distances, then stepped down for distribution to homes and businesses, all using AC. But interestingly, in recent decades, DC has made something of a comeback. Modern power, electronics allow us to efficiently convert between AC and DC, and to change DC voltages, something that wasn't possible in the 1890s. High-voltage DC transmission lines are now used for very long distances, and for submarine cables. And inside our homes, many devices, from computers to LED lights to smartphones, actually run on DC, with AC power being converted to DC at the device or in the wall adapter. So perhaps the War of the Currents never truly ended. Perhaps AC and DC have reached a sort of armistice, each used where it's most effective, working together in our modern electrical systems. By 1900, electricity had been harnessed. Generators turned mechanical energy into electrical energy. Motors turned electrical energy back into mechanical energy. Power grids were spreading across cities, bringing light and power to millions. But despite all this practical success, scientists still didn't really understand what electricity was at a fundamental level. They knew it could flow through conductors. They knew it came in positive and negative forms. They could measure its voltage, current, and resistance. But what actually was an electric current? What was moving through the wires? The answer came from a series of experiments conducted in the late 19th and early 20th centuries that revealed the existence of the atom's internal structure. In 1897, British physicist J.J. Thomson discovered the electron, a tiny negatively charged particle much smaller than any atom. He showed that cathode rays, mysterious rays produced in vacuum tubes, were actually streams of these electrons. This was revolutionary. Atoms, which had been thought to be indivisible fundamental particles, actually had internal structure. They contained smaller particles, and those particles were electrically charged. Over the next decade, physicists pieced together the basic picture of atomic structure. Atoms consisted of a tiny, dense, positively charged nucleus surrounded by a cloud of negatively charged electrons. Under normal circumstances, the number of protons in the nucleus equaled the number of electrons in the cloud, so the atom as a whole was electrically neutral. But electrons could be added or removed. An atom with extra electrons had a net negative charge. An atom with too few electrons had a net positive charge. And here, finally, was the explanation for electrical current. When you applied a voltage across a conductor, the electric field would push electrons through the material. The flow of electrons was your electrical current. This explained so much. It explained why metals were good conductors. In metals, some electrons were loosely bound and could move freely through the material. It explained insulators. In insulators, all the electrons were tightly bound to their atoms and couldn't move. It explained Benjamin Franklin's positive and negative charges. Positive charge was a deficiency of electrons. Negative charge was an excess of electrons. It even explained Franklin's unfortunate sign convention. Conventional electrical current is defined as flowing from positive to negative, the direction Franklin had established. But electrons, being negatively charged, actually flow from negative to positive, opposite to the conventional current direction. Franklin had gotten it backwards, a mistake that persists in our terminology to this day. The discovery of the electron and the development of atomic theory also explained chemical batteries like Volta's pile. The chemical reactions at the junction between the metals and the electrolyte were transferring electrons from one electrode to the other. The chemical energy of those reactions was being converted into electrical energy in the form of moving electrons. But the quantum revolution went even further. In the 1920s and 1930s, physicists developed quantum mechanics, a new theory of how matter and energy behaved at the atomic scale. This theory was strange, counterintuitive, but incredibly successful at predicting experimental results. Quantum mechanics revealed that electricity, at its most fundamental level, wasn't continuous. It was quantized, coming in discrete units. The charge of a single electron was the smallest unit of charge that could exist in isolation. You couldn't have half an electron's worth of charge moving through a wire any more than you could have half a coin in your pocket. This quantum nature of electricity has profound implications. It's the reason why computer chips work, why solar cells generate power, why LED lights shine. Modern electronics, the entire digital revolution that has transformed our world in recent decades, rests on quantum mechanical understanding of how electrons behave in semiconductors. And the quantum revolution is still ongoing. Physicists are now working on quantum computers, devices that use the quantum properties of electrons to perform calculations in radically new ways. They're developing quantum communication systems that use the quantum behavior of light to create absolutely secure transmissions. The story of electricity, it turns out, is far from over. Stand in your room tonight. Turn off all the lights. Imagine all the electrical devices around you suddenly ceasing to function. Your phone goes dark and silent. Your computer shuts down. Your refrigerator stops humming. Any heating or air conditioning falls silent. Streetlights outside go dark. Traffic lights stop working. Hospitals switch to backup generators. Water stops flowing because the pumps that move it through the pipes have stopped. Communication networks collapse. Within hours, modern civilization as we know it would begin to falter. This is how fundamentally electricity has transformed our world. It's not just that electricity is convenient or that it makes our lives easier, though it certainly does both. It's that our entire society, our entire infrastructure, our entire way of life has been built around the assumption that electrical power will always be available. Think about the journey we've traced tonight. We started with Thales of Miletus, rubbing amber with wool and observing that it attracted feathers. That was 2,600 years ago, and for most of the time since then, electricity was nothing but a curiosity, a mysterious property of certain materials that had no practical use whatsoever. William Gilbert investigated it systematically, gave it a name, distinguished it from magnetism. That was crucial scientific work, but it didn't change anyone's daily life. Benjamin Franklin proved that lightning was electricity, invented the lightning rod, developed the theoretical framework of positive and negative charges. The lightning rod saved buildings from fire, which was certainly valuable, but electricity was still not a source of power, not something you could use to do work. Then came the crucial breakthroughs. Galvani discovered that electricity could stimulate muscles. Volta invented the battery, providing the first source of continuous electrical current. Faraday discovered electromagnetic induction, showing how to generate electricity from mechanical motion. and how to use electricity to create motion. Suddenly electricity wasn't just interesting, it was potentially useful. But even then, for decades, electricity remained largely in the laboratory. It took the genius of inventors like Edison, Westinghouse, and Tesla, and the infrastructure they built, to actually bring electrical power to homes and businesses. It took the resolution of the War of the Currents to establish how electricity would be distributed, and it took thousands of less famous engineers and workers to actually string the wires, build the generators, and construct the grid. The transformation was astonishingly rapid. In 1880, electric light was a novelty, available only in a few experimental installations. By 1920, electricity was common in cities throughout the developed world. By 1950, rural areas were being electrified. By 1970, electrical power was nearly universal in developed countries, taken for granted, invisible. And what did electricity give us? Light, first and foremost. Artificial light that could turn night into day, that could allow factories to run around the clock, that could make reading and work possible at any hour. Before electricity, night was dark. Candles and gas lamps provided some illumination, but they were dim, dangerous, and expensive. Electric light was brighter, safer, and once the infrastructure was built, cheaper. But light was just the beginning. Electric motors replaced steam engines in factories, making manufacturing more efficient and precise. Electric trains and streetcars transformed urban transportation. Refrigeration became practical, allowing food to be preserved for long periods, transforming diet and health. Communication was revolutionized, first by the telegraph and telephone, then by radio and television, and now by the internet and mobile phones, all dependent on electricity. Medicine was transformed. X-rays powered by electricity allowed doctors to see inside the body without surgery. Electric lights and equipment made complex operations possible. Modern diagnostic equipment, from EKG machines to MRI scanners, all require electricity. In the developed world, it's hard to imagine modern medicine without reliable electrical power. And the revolution continues. The transition to renewable energy sources, solar and wind power, is essentially an electrical revolution. These sources generate electricity, which must be stored, distributed, and used efficiently. Electric vehicles are replacing internal combustion engines, converting our transportation system from one based on burning fossil fuels to one based on electrical power. The rise of artificial intelligence and machine learning is driven by massive data centers consuming enormous amounts of electricity to power their calculations. Looking forward, some of the greatest challenges facing humanity are electrical in nature. How do we generate enough electricity to meet growing global demand without destroying the climate? How do we store electrical energy efficiently so that renewable sources can provide reliable power? How do we extend electrical power to the billions of people in developing countries who still lack reliable access? These are not easy questions, but they're the questions we have to answer. Because electricity, this invisible force that ancient philosophers barely understood, that scientists slowly revealed over millennia, that inventors harnessed over decades, has become absolutely fundamental to human civilization. The journey from Thales amber to your smartphone is one of the most remarkable stories in all of human history. It involved thousands of people, from the most brilliant scientists to the line workers stringing electrical cables. It required not just scientific discovery but engineering ingenuity, business innovation, and massive infrastructure investment. And it's not over. The next chapters of the electricity story are being written right now in laboratories and factories and power plants around the world. As you lie there tonight, in your electrically lit room, perhaps charging your electrically powered devices, connected to the vast electrical grid that spans continents, you're part of that story too, so there you have it. The real story of how electricity was discovered. Not a single moment, not a single person, but a journey spanning millennia. From ancient Greek philosophers to Renaissance physicians, from lightning and frogs to batteries and generators, from laboratory experiments to globe-spanning infrastructure. If you found this journey through history fascinating, if you learnt something tonight, if you gained a new appreciation for the invisible force that powers your life, then please take a moment to hit that like button. It helps more people discover these stories. And if you want more deep dives into science and history, more journeys through the discoveries that shaped our world, then subscribe to the channel. There's so much more to explore. And drop a comment below. What surprised you most in this story? What do you think is the next frontier in electrical science? Where should we journey to next? Thank you for spending this time with me tonight. Until next time, stay curious, stay inspired, and remember, every time you flip a switch, you're tapping into one of humanity's greatest achievements, a triumph of curiosity, persistence, and brilliance that took thousands of years to achieve. Sweet dreams.